And if I show you the red curve, then you can do this. So now you see that this has moved forward 7 weeks. And if you think that there are not one contractor, but 15, 20, and they're doing 30 to 40 activities on each department or each space, then this accumulates very fast. And so you get much shorter durations with less labor. And these are exactly the kind of experiments we can do with discrete event simulation. Now I've only shown you here a very simple one with just one crew and 4 activities. But we can take it much further. We can say, what happens if we have a big building like this? 23 floors, 21,000 square meters, and it's built over an extended period of time. I imagine, and I'm guessing, that Professor Salvador tomorrow will show you the Empire State Building. Well, you have to now. And he will show you very accurately and ask you, why did it take so long to build one? Why does it take us today so long to build big buildings? Whereas the Empire State Building was built in a very short time. I'll leave him to tell you that tomorrow. So let's try and understand why it takes so long. Well, there are a lot of reasons, but one of the reasons is this. When you take what I guess I could call a laissez-faire strategy, and let the contractors do what they want, and they're earning cash flow for product, for production, for square meter or cubic meter or whatever, then what they tend to do, as I said before, in the small examples, open up spaces. That is represented here in the top diagram. These lines represent the progress of the structural crew, formwork, steelwork, casting, stripping, and so on. And those are pretty regular, and they're regular because the crews don't have a choice about where to go. You build floor after floor, and you build up, naturally. But the finishing works can be, let's just say, a mess. And they can be a mess because crews can work throughout the building practically wherever they wish. And not only that, when we have clients making changes to designs, interior changes to houses, apartments, whatever, to making choices about flooring, or in industrial work, suddenly realizing they need some other machine to be in that space, so let's make the floor thicker or something like that. There's noise in the process, and that interferes with the smooth flow of work. But if we adopt the width reduction strategy, and if we model it using a discrete event simulation, then you start to get results like this. And you see that the difference is that here, the work in any particular floor, like here or here, is bunched together so that we get shorter cycle times, more intense work to finish a product, get out of that product, remove it from the work in progress, and generally the results are much better. You can see that still the sequence is not necessarily one floor after the other, and that's because we use a strategy called process pull that I'll explain a little bit more about in a moment. So these are the good results. I can show you also that in this particular experiment, strategy A and C, we can compare, and you can see that it is about the duration in cycle time, but it's much more about the duration in standard deviation because work becomes more stable. It's less up and down and all over the place. And that, of course, makes management much simpler. A student just finished a much larger project where, not in terms of building, but in terms of the discrete event simulation. And in this project, apart from the case study and research and so on, we tried to compile a generic discrete event model of the construction of a building of this type. And the first interesting thing we found was that there is this notion of re-entrant flow, which it turns out is very common in manufacturing, especially things like semiconductor manufacturing, where a set of chips on a plate, on a disk, will go to etching and come back to lithography, go to something else, come back to etching, and so on, backwards and forwards. Well, we find that that's typical in construction too, where teams do something in a lab. Electrical workers, they put in some pipes that go away, they come back, they do some wiring that go away, they come back, they put the sockets on the wall and so on. So there are many similarities. Especially drywall, plumbing, electrical works and so on, have this typical behavior. Now what that does, and I'll show you that in a moment, what it does, it means that when teams begin work, when the drywall team works up a building, as soon as some spaces become available for closing the drywall, then the team that began goes back to where they began. And that's fine, because we want them to close out. But what happens then is that the electrician and the plumber and the others have no work. So you'll see them starting in cycles of interrupted flow of work. So we try to put together a more generic workflow simulator. It doesn't use critical path at all. In fact, you'll see tomorrow that the Empire State Building had no critical path. And indeed, there's no reason that a building should have one. A lot better without sometimes. So there is this generic model that when you come to a particular trade, you can fill it in with the detailed module of simulation. And in that way, you can simulate a lot of teams working in the same building under different conditions. The trade model for a single crew plugs into a project model. This over here, this activity workflow model instance is just one of those models I showed before. The details are not important, but the interesting thing is how I think effective a tool this can be, because what we find is what I tried to describe to you before is that here you see a drywall team working up, when as soon as they can go back down, they do go back down, and then the other teams have a break in their work. During this time, say from here to here, they're without work. They leave the site, they come back. It becomes chaotic rather than controlled. Now, the first intervention we can do here is a lean intervention that we call information pool or product pool. So what we do is we say, look at this, here's the black, the structure going up in a regular way. But these marks, the orange, they are the times at which clients bring information about individual apartments. So we say instead of having the work progress from the ground floor to the top floor, or from the first house to the last house in suburban development, we say, let's see if we change the sequence and we do the sequence of work according to the sequence that people bring us information. And if we do that, then we get this. Now you see that it's simply being reordered. The structure is now chaotic, but the flow of information is what's driving the rest of the finishing works. And so we have a break between the structure and the finishing works, but we're able to get very smooth, or I should say much smoother flows for the different work teams than we had before, with much fewer and shorter interruptions. But you still see that the reaction phenomenon still creates a problem over here. So then we introduce a second strategy that we call lean process flow, which is really pull. And here we're using a Japanese system called Kanban, when we don't allow people to work unless there are teams available to follow on from their work. So you don't do things unless it's useful, unless somebody can actually do something with the products you generate. And then we get this kind of result, which again is a whole lot smoother, and it results in much higher productivity for all of the teams. Partly I'm showing this to you to explain discrete event simulation, but I do have another agenda here, which is to set up what I want to explain in the next section, which deals with how we can use these ideas of managing flow in construction to make it much better. And so if we summarize the discrete event simulation, we can say that it's a very effective way to model construction operations. We can model the stochastic nature of events, even the chaotic nature of events, and we can model very complex relationships. They don't have to be simply finish-start or start-start or such things. They can be dependencies on equipment, dependencies on material, flows of information, and all sorts of other things. All of which brings me to the last chapter, which deals with the Kanban system. And I'm going to explain to you a little bit about the Kanban ideas, not so much for their own sake, but for the sake of showing you what our planned experiments where we bring together discrete event simulation, building modeling, and virtual reality together as a research method. So here's the background. We all know that the construction world is dynamic and full of uncertainty. We don't always know what's going to develop. And the result is that project managers are building buffers of time and money. So always a project manager, when they're asked to, or a contractor, when they're asked to estimate how much something will cost, then they'll say, well, 60, but let's say 80 to be sure, so we don't have to risk. And the same for the time, we'll add on some days or months or weeks, and in general these become self-fulfilling prophecies, right? It's partly because we don't